You know that feeling, right? You've poured your heart and soul into a new teaching strategy, maybe developed what you thought was the perfect learning material, or even tried to implement, I don't know, a brilliant new system in education,
Hmm.
only to watch it well, sputter and fall flat.
Oh, yeah. It's incredibly frustrating, isn't it?
Totally. You see the problem, you've brainstormed solutions, but that bridge between the great idea and actual consistent success in a real classroom,
Yeah,
it can feel impossible to build
they
sometimes.
really can.
What if there was like a powerful approach designed specifically to merge that practical problem solving with rigorous research, something to help you actually cross that bridge?
Yeah, something like that would be amazing. It's almost like needing a crystal ball,
Yeah.
to see if your educational tool will actually succeed, not just in theory, but in real, messy classrooms.
A crystal ball. I love that image. Welcome, everyone, to the deep dive. Today, we're plunging into a fascinating field called educational design research, or EDR for short. And this isn't just another, dry research methodology.
Not at all.
Think of it more like a blueprint for creating educational solutions that actually work in the real world. And for you, our listener, with your invaluable background in elementary education and maybe your burgeoning interest in product development, this deep dive is going to be incredibly insightful, I think.
That's right. EDR is really the bridge you might be looking for. It connects your deep classroom experience, all that practical knowledge,
Mhm.
with the exciting, maybe sometimes overwhelming world of designing truly effective educational tools. It sort of offers a shortcut to understanding how research can directly inform and refine and really elevate your future designs, making sure they resonate with the specific needs of young learners and, of course, the educators guiding them.
So our mission today is basically to unpack EDR. How did it even emerge? What does it actually involve? And why is it so vital for anyone looking to make a genuine research-based impact in education? We'll show how it's not just for academics hidden away somewhere, but a practical, iterative process that can literally transform how you approach developing educational materials or programs, especially for elementary school kids.
Exactly. And we've drawn on some really rich material today, mainly from pioneers in this field, experts like Jared Plump and Ninke Naveen. Their work really forms the backbone of understanding why EDR came about and how it functions as this essential tool for creating impactful educational interventions.
Okay, so let's start with a big problem that educational research often faced in the past. You mentioned pioneers. What were they reacting against? The source material highlights this feeling that traditional research often felt divorced from the problems and issues of everyday practice.
That's a key phrase.
It led to this credibility gap. Why were researchers feeling this disconnect? What was missing from those, older approaches that made them feel so separate from classroom realities?
It's a great question, and it really gets to the core issue. The problem wasn't that traditional research methods, think large-scale experiments, surveys, correlational analyses, were inherently flawed. They weren't. They're actually excellent for describing a phenomenon. So a survey can tell you what the problem is, or maybe how prevalent it is, or even who is affected. That's useful info.
Right.
But as leading researchers like Van den Akker pointed out, they rarely provided the prescriptions that were truly useful for design and development problems in education. They told you what needed attention, but not clearly how to fix it.
Yeah.
You know,
Okay. So it's like identifying the illness, but not suggesting a cure.
exactly. That's a great analogy.
Mhm.
It meant that ambitious educational reforms, or even just small practical classroom improvements, couldn't just be developed at the drawing tables in government offices or in university labs and then simply dropped into schools expecting them to work perfectly. There was a critical piece missing: that practical, research-informed guidance for actual implementation and, crucially, continuous refinement in real-world settings.
I can absolutely see how that disconnect would be incredibly frustrating. And for someone like you, our listener, maybe moving from the classroom into product development, it immediately raises a critical question, doesn't it? How do you make sure the products you create are directly solving real, tangible problems faced by teachers and students in elementary settings? Not just being a nice, theoretically sound idea that, ultimately collects dust because it's simply not practical on a Tuesday morning.
Precisely. That gap, that frustration, was exactly what EDR aimed to address.
Okay, so let's make it concrete. Think about an elementary classroom.
Okay, let's take fractions, a perennial challenge. So imagine a traditional study. A big survey might reveal that, say, third graders are significantly struggling with understanding fractions. This study could give you incredibly detailed data. how many students are struggling, maybe which specific fraction concepts are the hardest, like comparing fractions with different denominators, perhaps. It might even show correlations between that struggle and, say, their prior knowledge of multiplication. All of that is valuable descriptive information, no question. But here's the crucial point. It wouldn't tell you, as a product developer trying to help those kids and their teachers, how to design a new fractions curriculum or a game or manipulative that directly addresses those struggles in a practical, usable way for a busy elementary teacher. It wouldn't give you the blueprint for the lessons, the hands-on activities, or the assessment tools that would actually make a difference on the ground, the middle of a hectic school day.
Got it.
That's precisely where EDR steps in. It's all about moving beyond just identifying the problem to systematically designing, developing, and refining the solution until it actually works in the real world.
So if traditional research often tells us what the problem is, what's EDR's big mission then? What does it actually do? Is it just about fixing those immediate problems, or is there something more going on?
That's a sharp question.
Yeah.
And yes, there's definitely more to it. At its heart, EDR has this clear dual mission, or a twofold purpose, as they often call it. First, yes, absolutely. It's about developing research-based solutions to complex problems in educational practice. So fixing things in the real world is key.
Okay, solving problems.
But simultaneously, its second purpose is to develop or validate theories about learning processes, learning environments, and the like. It's not just about solving an immediate problem, like the fractions issue. It's also about understanding why those solutions work and building generalizable knowledge from that whole process.
Ah, okay, so it's practical and theoretical.
Exactly. If we connect this to the bigger picture, EDR systematically studies the design, development, and evaluation of what are called educational interventions.
Right.
And just to be clear, intervention is a really broad, flexible term. It's like a container term, as some researchers put it, for pretty much anything you design and develop.
Like what?
Well, it could be a new curriculum, a specific learning process, a physical learning material like those fraction tiles, a digital product, an app, or even an entire school-wide system for, say, positive behavior support.
So if I'm creating a new reading app for kindergartners, or that science kit for fourth graders, or even a professional development program for teachers, those are all intervention.
Yeah, all interventions. And EDR is essentially an applied science that consciously bridges that gap we talked about, the gap between abstract theory and practical application. It's about taking theoretical insights about how kids learn or how teachers teach best and molding them into tangible tools that function effectively in real-world elementary classrooms.
Can you give us an example of this twofold purpose in action, especially for someone thinking about developing products for elementary kids?
Certainly. Let's take a really common challenge in elementary education: differentiation. Teachers often struggle, understandably, to provide truly differentiated reading practice for students with widely varying reading levels all within a single classroom.
Oh, absolutely. You've got 25 kids, some reading way below grade level, some way above.
Exactly. And the teacher has maybe 20 minutes for guided reading groups. It's a huge challenge. Now, an EDR approach would tackle this head on. Its first purpose would be to design, let's say, a digital reading platform that adaptively adjusts to individual student levels. This platform is the research-based solution to that differentiation problem. You develop the platform itself, you'd iterate on it, refine it based on teacher and student feedback until it effectively helps teachers manage differentiation and helps students engage with content at their own level. That's the practical, usable solution, the first goal.
Okay, makes sense. So where does the second purpose come in, the theory part?
Right. Here's where it gets interesting. While you're developing and testing this platform, you're also systematically studying how these young students engage with adaptive technologies. You're not just seeing if it works, but how and why. You're observing what specific features truly support their reading growth. For example, does immediate audio feedback on pronunciation work better than just visual cues for early readers? Does a certain type of reward system keep second graders more engaged than another?
Ah, I see.
This deliberate study helps you build generalizable design principles, we'll talk more about those later, about effective adaptive learning for young children. This knowledge can then inform not just future versions of your product, but potentially other adaptive learning products across the elementary landscape. So you're fulfilling that second purpose, developing or validating theory about how kids learn with these tools. You're not just making a great tool, you're generating knowledge about how to make great tools for this specific context.
That example really clarifies how you're both building a solution and building knowledge at the same time. Okay, so EDR has this dual function. How does it fit into the broader landscape of research? You mentioned surveys, experiments. What makes EDR different? What sets it apart?
Well, the main thing that sets EDR apart is its primary function. Its core purpose is to design and develop. While a survey might describe a phenomenon, or a case study might explore a specific instance in depth, or an experiment might compare the effects of two different teaching methods, EDR is unique because it's actively building something new.
It's constructive.
Exactly. It's not just observing existing conditions, it's intervening directly in the educational landscape. It's about creating an intervention, that tool, that program, and then rigorously studying that intervention's development and its impact as it evolves.
That seems absolutely critical for you, the listener, as a potential product developer. If your ultimate goal is to create something tangible for elementary classrooms, a new math game, a literacy program, whatever it is, EDR isn't just like a useful tool. It sounds like the most direct and effective path.
It really is. And it acknowledges that while a research project's main goal might be design and develop, other research functions often serve it. They play supporting roles.
How so?
Well, for example, before you even begin designing, say, a new classroom behavior management app for first graders, you might first need to conduct some descriptive research, maybe surveys or interviews with teachers, to really understand and carefully define the current challenges they face with transitions or managing behavior.
Okay, so you described first.
Right. Or, once you've developed an early prototype of your app, you might use evaluation research methods to assess its initial effectiveness or usability. But the core, the driving force, remains the act of building and refining that solution.
Got it. And you mentioned earlier that even within EDR itself, it's not just one single approach. There are different types.
Precisely. And researchers in the field generally delineate two main types: development studies and validation studies. It's important to understand the nuance between them because, while related, they have slightly different primary aims.
Okay, that sounds like a key distinction. Can we break down the difference between development studies and validation studies?
Absolutely. Let's start with development studies. Here, the primary purpose is really clear. Develop research-based solutions to complex practical problems in education. This is sometimes called research-based design. So, for example, if the problem is that elementary teachers lack engaging, hands-on materials for teaching, say, magnetism, a development study would focus intensely on creating a fantastic, effective magnetism kit. That's the main goal. But simultaneously, while you're doing that, you're also systematically advancing knowledge about how to design and develop interventions, like that kit. You're meticulously documenting your process, figuring out what design choices work and why, in order to generate generalizable insights or principles for future design efforts in science education.
Okay, so the product is central, but you're learning design lessons along the way. What about validation studies?
Validation studies, on the other hand, have a slightly different emphasis. Their main purpose is the development or validation of a theory about learning processes or environments. This is often referred to as design-based research.
Design-based research.
Okay. Here, the educational intervention you create isn't just the end product. It often becomes a kind of test bed, almost like a laboratory but in a real-world setting, for exploring and refining your theoretical understanding of how learning happens. The intervention is intentionally designed to create a specific learning situation or ecology, and the research focuses intensely on understanding the underlying theoretical mechanisms at play within that situation.
So the intervention is more like a tool for studying the theory.
In many ways, yes. The product is important, of course, but its main role in a validation study is often to facilitate the investigation of the theory itself.
That distinction is really helpful. Could you give us a concrete elementary example that clearly differentiates between the two? Let's say I'm interested in physical manipulatives for young kids.
Okay, perfect. Let's stick with math manipulatives for early grades. For a development study, imagine you're creating a brand new math manipulative designed to help kindergartners grasp early number concepts, specifically subitizing, that ability to instantly recognize the number of objects in a small group without counting one by one.
Right, like seeing 3 dots and just knowing it's 3.
Exactly. The primary goal here is the manipulative itself.
Yeah.
Making it effective, durable, engaging, and usable by both kindergartners and their teachers. That's job number one. But along the way, as part of the EDR process, you would systematically document how you designed it, what materials worked best, what visual arrangements seemed to support subitizing better than others, maybe what iterations failed and why. The theoretical yield from this would be those design principles for future manipulative development for early childhood math. For instance, you might generate a principle like, Manipulatives for subitizing in kindergarten should use irregular dot patterns to encourage pattern recognition over rote counting, rather than relying solely on standard dice patterns.
Okay, so the principle comes out of the process of making the thing work well.
Exactly. Now, for a validation study, the focus shifts. Let's say you're exploring how collaborative problem solving happens among, say, fifth graders, when they use a specific type of digital tool that allows them to co-create virtual models of historical events.
Okay.
Here, your intervention, the digital tool and the specific activity structures you design around it, is primarily a means to an end. It's designed very intentionally to create a particular learning environment where you can study deeply the theory of how collaboration in that digital space leads to, perhaps, deeper historical understanding or better argumentation skills. You're trying to validate or refine a theory about sociocognitive processes using the intervention as your research instrument. The digital tool needs to work, but its main role is to let you investigate the theory in action.
That makes the difference much clearer. And this idea of getting both a product and knowledge, this is where it gets really exciting for product developers, right? It sounds like a kind of superpower.
Maybe not a superpower, but it's definitely powerful.
It means you're not just building one product, you're building knowledge that fuels your next 10 products. It's what the researchers call the twofold yield. You get a usable, effective intervention, and you contribute to the body of knowledge through things like design principles.
That's precisely it. This means you're not just creating, say, a great reading app or a fantastic science curriculum. You're also generating generalizable knowledge.
Yeah.
These are the how-to guidelines, the heuristics that can inform other designers facing similar problems down the road. It essentially transforms those implicit design decisions you might make intuitively during development into explicit, well-articulated, research-backed guidelines. It's like turning your hands-on experience into a repeatable formula that others can learn from and build upon. It really elevates your work from just a one-off creation to something that contributes more broadly.
Can we get another illustrative elementary example of this twofold yield? Let's go back to that adaptive reading platform.
Okay, perfect. So you develop that adaptive reading platform for elementary students struggling with differentiation. The first, most obvious yield is the functional, effective platform itself. Teachers can use it. Students are learning from it. It solves the initial problem. That's your tangible product. That's yield number one.
The thing you can sell or implement.
Right. But the second and arguably equally valuable yield is the systematic documentation of the design principles you uncovered during its creation. For instance, after numerous cycles of prototyping, testing with K2 students, observing their interactions, interviewing teachers, you might arrive at a principle like this. If you want to design an adaptive reading platform for K2 students, then it is best advised to include audio pronunciation support for every new or challenging word presented on the screen, and to use simple, non-distracting animations as positive reinforcement after correct responses.
Okay, specific features.
Because this combination directly supports early phonological awareness development, which is critical at this age, and it helps maintain intrinsic motivation for young learners who might otherwise get easily discouraged. See? These principles are incredibly valuable. They explain why certain features work, under what conditions they work best, and for whom. That's knowledge you can use for your next project and share with the field.
That makes so much sense. It's like distilling the secret sauce of successful design into a shareable recipe. Okay, so beyond its definition and this twofold yield, what are the core characteristics that truly define EDR? What's its DNA, making it distinct and powerful?
Yeah, the field highlights several key characteristics that are really the heartbeat of EDR. They make it stand apart from other ways of doing research. First, it's inherently interventionist. What this means is the research actively aims at designing, developing, and implementing an intervention in a real-world setting. You're not just standing back and observing, you're creating something and intentionally changing the environment. If you're developing that new game to teach sight words, you're making the game and putting it into classrooms to see its effect and refine it based on that.
You're getting your hands dirty.
Exactly. Second, and this is absolutely crucial, it's profoundly iterative. It incorporates these continuous cycles of analysis, design, development, evaluation, and revision. Think of it as constant refinement, a spiral upwards. You build a prototype. You test it with real users, kids, teachers. You learn what needs fixing or improving. You revise it, and you test it again. This loop continues until you achieve a good balance between your ideal design and what's actually practical and effective in the classroom.
Constant tweaking based on feedback.
Right. Third, it's process-oriented. The focus isn't just on the final outcome, like did test scores go up. It's also on understanding how and why the intervention works, or maybe why it doesn't work. It's not a black box where you just measure input versus output. You want to unpack the mechanisms, the steps, the interactions within the intervention that lead to the observed outcomes.
Understanding the journey, not just the destination.
Well put. Fourth, it's highly utility-oriented. This means the design's merit, its quality, is measured significantly by its practicality and usability for the actual users in their real contexts. Is it actually usable by busy elementary teachers juggling a million things? Can young students navigate the app or materials independently, or does it require constant adult help? This is where your background in elementary education is so vital. You inherently understand the practical realities and constraints of a classroom.
Yeah, that's critical. What else?
Fifth, it's theory-oriented, even while being practical. Designs are typically based on some conceptual framework or existing theories about learning. You don't just start from scratch. And importantly, the systematic evaluation of your prototypes as they evolve contributes back to theory building. It's this continuous dialogue between theory and practice, where each informs and refines the other.
So it's grounded in research, and it feeds back into research.
Correct. Sixth, there's almost always a strong involvement of practitioners. This means active participation or collaboration with teachers, maybe school leaders, and often the students themselves throughout the entire process. This isn't just helpful, it's usually essential. It dramatically increases the relevance and practicality of the intervention, making it far more likely to be successfully implemented and sustained. If you're designing something for the classroom, the people in the classroom really must be part of the design team, ideally from day one.
Makes sense. Anything else?
And finally, it's often multi-leveled. EDR frequently links what's happening at the classroom level, the teacher-student interaction, the use of materials to broader structures, like the school's overall policies, the district's curriculum guidelines, or even community resources and parental involvement. A new math program for third grade, for instance, might need to consider not just student learning, but also things like school-wide assessment schedules or the district's available technology infrastructure. It recognizes that classrooms don't exist in a vacuum.
Those characteristics really paint a comprehensive picture. Let's try and apply some of these to elementary classroom scenarios to make them even more concrete, particularly that iterative nature, the practitioner involvement, and being process-oriented. How would those look?
Excellent idea. Let's take the iterative characteristic first. Imagine you're developing that new hands-on science experiment kit we mentioned, maybe for fourth graders, focused on the water cycle. First, you'd analyze the learning goals, maybe identify common misconceptions fourth graders have about evaporation or condensation. Then you design a basic version of just one experiment in the kit, say, creating a mini water cycle in a Ziploc bag taped to a window.
Okay.
You try this basic version with just one small group of students. That's an initial small-scale evaluation. You observe them closely. Are they engaged? Are the instructions clear? Are the materials working as expected? Maybe you see that the instructions are confusing, or the Ziploc bags keep leaking, or maybe the activity doesn't actually seem to help them grasp the concept of condensation visually.
So you see the problems right away.
Right. Based on these observations and maybe talking to the kids, you revise the kit. That's the design development part. You might rewrite the instructions with simpler language and add diagrams, find better quality bags, maybe add a step where they use ice cubes to enhance condensation visibility. Then you try the revised version again, maybe with another small group. This cycle of design, test, analyze, revise, retest repeats until that specific experiment is polished and effective.
Got it. Iteration in action. What about practitioner involvement?
Okay, for practitioner involvement, let's think about designing, say, a digital app to help kindergarten teachers manage classroom transitions more smoothly, like moving from circle time to centers. You wouldn't just build this app in your office and then hand it over.
No, that probably wouldn't work well.
Definitely not. From day one, you're bringing in real kindergarten teachers. You're interviewing them about their biggest transition challenges, what strategies they currently use, what features in an app would genuinely save them time or reduce chaos. Then you show them early, maybe even just hand-drawn mock-ups of the app. You get their feedback. Then you build a very basic functional prototype and have them actually try using it during a transition in their real classroom for a day or two. Their immediate feedback is invaluable. They might tell you, this timer sound is too jarring, or I need a way to quickly see which center still has openings, or the login process is too slow when I've got 25-year-olds waiting.
Real-world feedback.
Exactly. This deep collaboration ensures the app is truly practical and tailored to their incredibly busy, dynamic days. It prevents you from building something that looks cool, but is ultimately unusable or doesn't solve their actual problem.
Okay, and finally, being process-oriented.
Right, process-oriented. Let's say you're developing a new social-emotional learning, SEL, curriculum for second graders, aiming to improve empathy and conflict resolution skills. You're not just going to measure outcomes like, did referrals to the principal's office decrease? Or did students score higher on an empathy questionnaire at the end of the year? While those final outcomes are important, a process-oriented approach means you're also observing how the SEL lessons actually unfold in the classroom.
What's happening during the lesson itself?
Exactly. You're looking at things like, what kinds of discussions are students having during the activities? How are teachers facilitating those discussions? Are they asking good, open-ended questions? What specific activities seem to genuinely lead to students demonstrating empathy or attempting to resolve conflicts peacefully amongst themselves later on? You try to understand the process of learning, the causal mechanisms at play, not just the end result. This deeper understanding of the how and why is what allows you to refine those specific activities to be even more effective and eventually build those generalizable design principles about teaching SEL effectively to second graders.
Those examples really hammer home how deeply embedded these characteristics are, especially that iterative nature. It's crystal clear now that EDR is fundamentally cyclical in character, this constant loop, this spiral of analysis, design, evaluation, and revision. We see this core idea reflected in various models researchers use, like Plomp's simplified diagram or Weidman's generic design research model.
Absolutely. And what's immediately striking about EDR, especially when you look at models like Weidman's, is how it perfectly illustrates this dynamic reciprocal relationship. You have this successive approximation of practical products, meaning your intervention, your tool, gets progressively better and closer to the ideal through testing and refinement.
Okay, the product improves.
Right. And working hand in hand with that, you have a successive approximation of theory. As your product gets better and more refined, your understanding of why it works, the underlying design principles, the theoretical insights, also become clearer, more robust, and more refined.
So they improve together.
Exactly. It's a continuous, simultaneous improvement of both the practical solution and the theoretical knowledge that explains and supports it.
That dynamic relationship between the product and the theory, that really seems to be what distinguishes EDR from just, simple trial and error tinkering.
Precisely. You're not just fixing something until it seems to work. You're systematically learning why it works and building generalizable knowledge at the exact same time. You're essentially designing and studying simultaneously.
Okay, so within this overall cyclical nature, researchers generally outline some main phases for most EDR projects, particularly development studies. What are they?
Yeah, typically you can think of three broad phases, although the lines can blur a bit because of the iterative nature. These are often described as preliminary research, development or prototyping, and assessment.
Okay, preliminary research, development, prototyping, and assessment. Can you walk us through them?
Sure. Each phase has a distinct focus, logically building upon the last one. So first is preliminary research. Think of this as laying the groundwork, building your foundation. It involves a really thorough needs and context analysis, basically. What problem are you actually trying to solve? For whom? And in what specific educational environment or context? What are the constraints and resources?
Understanding the landscape.
Exactly. You'd also conduct a comprehensive literature review, what's already known about this problem. What existing theories or interventions might be relevant? What have others tried? And finally, based on all that, you develop an initial conceptual or theoretical framework, your guiding set of ideas, assumptions, and maybe initial design hypotheses for the intervention. It's your deep dive into the problem before you even start sketching out solutions.
So lots of homework up front.
Definitely. Then comes the development or prototyping phase. This is where that iterative magic we've been talking about truly happens. It consists of multiple microcycles of research. And within these cycles, formative evaluation is the most critical activity.
Formative evaluation, meaning evaluation during development.
Exactly. You're constantly gathering feedback and data from small-scale tryouts of your prototypes to inform the next round of revisions. You're not waiting until the very end to see if it works. You're continuously improving it along the way, refining the design based on evidence. This is where the bulk of the hands-on design, building, testing, and redesigning occurs.
The messy middle, maybe?
Sometimes. But it's where the real learning and improvement happen. And finally, there's the assessment phase. This involves what's typically called a semi-summative evaluation. The main goal here is to check if the now relatively mature intervention meets its predetermined specifications and actually achieves its desired outcomes in a more conclusive, often larger scale way than the formative evaluations.
So does it work as intended?
Pretty much.
Yeah.
But notice the semi part. While it's about concluding if your solution works, this phase often still leads to recommendations for further improvement, refinement for different contexts, or guidance for broader implementation. So even a final assessment often feeds back into the cycle, maintaining that iterative spirit. It's rarely a definitive the end.
That makes sense. Okay, let's make this concrete again with an illustrative example. Let's go back to developing that elementary science kit, maybe for second graders who are struggling with abstract concepts like ecosystems. How would these three phases actually play out in real life for that project?
Okay, great example. Let's say our identified problem is that second graders struggled to grasp abstract concepts like ecosystems because the current materials are too textbook heavy, lacking concrete hands-on experiences. So the preliminary research phase, you'd start by maybe observing several second grade science lessons. You'd interview teachers about their specific frustrations teaching ecosystems and what materials they currently use or wish they had. You definitely research existing science kits or curriculum units for this age group, noting their strengths and weaknesses based on reviews or studies. You dive into the research literature on how young children learn science best, maybe looking at theories about concrete operational thinking or inquiry-based learning. From all this information, you might decide your conceptual framework will be centered on hands-on, inquiry-based learning, meaning the kit must encourage active exploration and discovery rather than just passive information reception. That's your foundation.
Okay, groundwork laid. Now the development phase.
Right. Now, the development prototyping phase, this is where you go through those iterative microcycles, building from simple ideas to more refined prototypes. Iteration 1. Maybe you start with just a paper prototype. This could be sketches of the kit components, maybe a detailed lesson plan outline for one activity, like building a mini terrarium. You show these initial ideas to a few second grade teachers. You ask them, is this concept clear? Would this activity sequence work in your classroom? Are the suggested materials feasible? This is early formative evaluation, focused heavily on expected practicality and the consistency of your idea. You revise your plans based on their initial feedback. Maybe they point out safety concerns or suggest simpler materials.
Getting teacher input right away.
Absolutely. Iteration 2. You then gather some simple, inexpensive materials and create a basic physical prototype for just one key activity from the kit. Let's stick with building that mini terrarium. You then try this activity out with a small group of second graders, maybe just 4 or 5 kids. You observe them very closely. Are they engaged? Are they following the instructions? Are they actually talking about producers and consumers or just playing with dirt? You might interview them briefly afterwards. What was fun? What was confusing? What did you learn? Maybe you discover the instructions are still too wordy, or the tiny seeds are too hard for them to handle, or the connection between the terrarium and a real ecosystem isn't clear to them. Based on this direct observation and feedback, you go back to the drawing board and redesign that activity.
Learning from the kids themselves.
Crucial. Iteration 3. You revise the instructions, maybe add pictograms, find larger seeds or pre-sprouted plants, perhaps create a simple chart comparing the terrarium parts to a forest ecosystem. You then try this refined version with another small group, maybe even observing it being used within a real classroom setting during science time. You continue this cycle of testing, analyzing the results, refining the design, and retesting. You do this for each component of the kit until they are demonstrably effective and practical.
So multiple rounds of refinement.
Right.
Then what?
Then you move to the assessment phase. After several iterations have produced a solid, well-tested prototype of the entire science kit, you'd conduct a larger trial. This might involve implementing the full kit in several different second grade classrooms, perhaps over a period of a few weeks or a whole unit. Here, you collect more formal data on student learning outcomes, maybe through pre- and post-unit assessments of their ecosystem knowledge, analyzing their science journal entries, or observing their ability to explain concepts. That's assessing effectiveness. You'd also collect data on teacher ease of use and fidelity of implementation, maybe through teacher surveys, implementation logs, or interviews. That's assessing practicality. Even at this stage, while you're aiming to conclude if your kit works as intended, you're likely still gathering valuable feedback for final tweaks, maybe improvements to the teacher guide, or recommendations for how to best support teachers using it in different school contexts. It's a comprehensive reality check before considering wider dissemination.
That detailed breakdown of the phases is incredibly helpful for visualizing the whole iterative journey. Okay, so we've talked about the process of building and refining, but once you've built your intervention, how do you actually judge its quality? How do you know if it's actually any good? Are there specific benchmarks or criteria?
That's a fundamental question, and yes, there are. Researchers in EDR, particularly in Yank and Nevin, have outlined some widely accepted generic criteria for evaluating the quality of educational interventions. These are often framed as validity, practicality, and effectiveness. Think of them as the three pillars of quality.
Validity, practicality, and effectiveness. Okay, let's break those down. What does validity mean in this context?
Validity here really has two key aspects. First is what's sometimes called relevance, or content validity. This means the intervention should clearly address a real significant need or problem in education, and its design should be based on sound, up-to-date knowledge, relevant theories, research findings. For instance, if you're designing that phonics program, is it addressing documented literacy challenges, and is it informed by current scientific understanding of how reading develops?
So is it needed, and is it based on good science?
Exactly. The second aspect is often called consistency or construct validity. This means that all the components of the intervention should be logically linked and internally coherent. Does your phonics program build skills in a sensible, evidence-based sequence? Are the learning activities clearly aligned with the stated learning goals? Is the assessment matched to the instruction? If an intervention meets these requirements, it's relevant, theory-based, and internally consistent. It's considered valid in its design.
Okay, that makes sense. What about practicality?
Practicality is all about usability in the real world. The core question is the intervention usable and feasible for the target users, teachers, students, maybe parents, to implement and use as intended in their actual settings?
Like, can they actually do it?
Precisely. For elementary education, this means things like, can busy teachers easily understand and implement this new curriculum unit without needing weeks of specialized training? Can young students navigate the educational app independently, or does it require constant teacher support? Is it affordable and manageable within typical school budgets and schedules? It's all about the feasibility and user-friendliness in the day-to-day reality of schools and classrooms.
Got it. And the third pillar was effectiveness.
Right, effectiveness. This is probably the one people think of most often. It's fundamentally about outcomes. Does the intervention actually achieve its desired goals? Does it lead to the intended improvements in student learning, or changes in behavior, or increased engagement, or whatever specific outcomes it was designed to produce? This is the ultimate does it work question. Does it make a meaningful difference?
Okay, those three seem like fundamental pillars. You also mentioned something interesting earlier, an implied hierarchy.
Yes. The way these criteria are often discussed implies a kind of logical hierarchy or dependency. Think about it. Niveen and others suggest if an intervention is not practical, why would it make sense to investigate its effectiveness?
Right. If teachers can't even use your fancy new math game because it crashes constantly or takes an hour to set up, it doesn't matter how theoretically effective it could be in improving math skills. They won't get that far.
Exactly. And similarly, if an intervention is not well designed, meaning it's not consistent or valid in its construction, why would it make sense to investigate its practicality? If the concepts in your science curriculum jump around illogically, or the activities don't actually align with the learning goals, it's unlikely to be practical for anyone to teach or learn from effectively, even if the materials themselves are easy to handle.
So it suggests a kind of step-by-step approach to ensuring quality. You need a valid design first, then ensure it's practical to use, then you can meaningfully assess its effectiveness.
That's the general idea. You build the quality in layers throughout the EDR process.
Okay, that makes perfect sense. Now, the source material also makes an important distinction between expected versus actual practicality and effectiveness. What's the difference there, and why does that distinction matter so much for someone developing educational products?
Yes. This is a huge and sometimes painful reality check for product developers. Expected quality refers to what you anticipate will happen based on things like expert reviews, maybe feedback from focus groups, analysis of the design on paper, or your own internal assessments before real-world use.
So what you think will happen.
Right. You expect your new reading app to be practical because a few experienced teachers looked at the mock-ups and thought the interface looked intuitive. You expect it to be effective because it's carefully aligned with solid research principles on reading instruction. These are informed predictions.
Okay. And
Actual quality refers to what truly happens when real users, those teachers, those students, maybe even parents, actually use the intervention in their real, messy, unpredictable settings over a period of time. Only a genuine field test, pilot study, or extended use in real classrooms can truly reveal the actual practicality and actual effectiveness. Expert appraisals and theoretical analyses are valuable for estimating expected quality, but they simply cannot substitute for evidence gathered from real-world application.
That's why those iterative cycles in real classrooms are so non-negotiable in EDR.
Absolutely vital. That's where the rubber meets the road.
Can we illustrate that expected versus actual difference with another elementary example, maybe that online math game for first graders?
Sure thing. Let's say you've designed a fun online game for first graders, focused on mastering addition facts up to 20. For expected practicality, you might hold a demo session for a few experienced first-grade teachers. They click through the game, review the teacher dashboard, look at the curriculum alignment. Based on their expertise in this controlled viewing, they say, yeah, this looks great. It seems easy for the kids to navigate, and the reports look helpful for me. They expect it to be practical.
Okay, thumbs up based on the demo.
But then you move to assessing actual practicality. You implement the game in those teachers' classrooms for a couple of weeks. Now, reality hits. You might find that teachers struggle because the game requires individual student logins and managing passwords for 25 6-year-olds is chaotic. Or maybe the game runs really slowly on the older school computers. Or perhaps the sound effects, which seem fun in the demo, are actually really distracting in a busy classroom. Or maybe the game requires too much one-on-one teacher help when a student gets stuck, pulling the teacher away from other groups. These are the actual practicality issues that only surface during real use and are critical to fix for the game to be truly usable.
Oof, okay, I can see that. What about effectiveness?
Same distinction applies. For expected effectiveness, based on the game's design, maybe it uses spaced repetition, provides immediate feedback, aligns perfectly with learning theories. For math facts, you and the expert reviewers expect it will significantly improve first graders' addition fact fluency. It should work, based on the design.
Makes sense on paper.
However, after a month of consistent use in those classrooms, you look at the actual effectiveness data. You might analyze pre- and post-test scores on fact fluency, or track student progress within the game itself. Maybe the results show only minimal improvement overall, or perhaps the game only seems to help students who are already pretty good at math facts, but doesn't help the struggling learners much. Or maybe kids get bored after the first week. This is your actual effectiveness data. The game might be practical enough now, but if it's not truly moving the needle on the intended learning outcomes for the target students, it still needs further iteration on the instructional design aspects.
Wow. That gap between expected and actual, that really highlights why you can't just design something in a lab and expect it to work perfectly in the wild.
Exactly. That gap is precisely where the most valuable learning and refinement often occurs in the EDR process. It's where you gather the critical feedback needed for genuine, impactful improvement.
Okay, so we have these criteria: validity, practicality, effectiveness. And we know they have a hierarchy, and we need to look at actual versus expected. Do these criteria carry the same weight throughout the whole EDR process? Or does the emphasis shift across those phases we talked about: preliminary, development, assessment?
That's a great question. And no, the emphasis definitely shifts logically as the intervention develops. Think of it like a spotlight moving across the criteria depending on the phase. The source material, particularly Nevin's work, often shows this in tables.
Okay, so how does it shift? Where's the focus in the preliminary research phase?
In the very beginning, the preliminary research phase, when you're just exploring the problem and formulating initial ideas, the primary emphasis is heavily on relevance. Is there a real, documented, pressing need for this intervention? Are you addressing the right problem that educators and students actually care about?
Establishing the why.
Exactly. You also pay significant attention to consistency. At this stage, does your initial conceptual framework or your first rough idea for the intervention make logical sense? Is it internally coherent based on existing theory and knowledge? At this early point, you're generally not testing effectiveness at all, and practicality is usually only a minor theoretical consideration like, could this theoretically be used in a classroom?
Okay, so relevance and consistency are key early on. What happens in the development prototyping phase?
As you move into the development or prototyping phase, especially during those initial iterative cycles with early prototypes, your focus shifts. Now, you're still concerned with consistency. Does the actual design logically hold together? Are all the newly designed parts aligned with your conceptual framework? But crucially, practicality becomes paramount. Can people actually use this prototype? Is it user-friendly for both teachers and students in a realistic way? You get lots of feedback on usability.
Makes sense. You need to know if people can even interact with it.
Right. Then as you refine the prototypes through subsequent iterations and they become more stable and complete, effectiveness gradually becomes more important. You start asking more seriously, Is this refined version actually starting to make a difference in student learning outcomes or behavior, even on a small scale? You might start collecting some preliminary effectiveness data.
So practicality first, then effectiveness emerges as you refine.
Generally, yes. Finally, the assessment phase, when you have a relatively mature and stable version of the intervention, the spotlight shifts squarely onto demonstrating actual practicality and actual effectiveness in real-world conditions. This is where you conduct the more rigorous, often larger-scale trials, specifically designed to confirm if your product achieves its intended goals for its target users in typical classroom settings. You're seeking robust evidence for both usability and impact.
Okay, so connecting this to the product lifecycle of, say, a new reading curriculum for early elementary grades. In the initial brainstorming and needs analysis, you're laser focused on, is this relevant to the real reading challenges K-1 teachers and students are facing? And is our overall pedagogical approach consistent with the science of reading? As you start creating individual lessons or units, you're constantly testing their practicality in classrooms through tryouts. Can teachers deliver these lessons easily? Are the materials manageable? Are students engaged?
Right, getting that user feedback.
Only when a full unit, or maybe even a semester's worth of material, is developed and used consistently for a longer period, do you rigorously assess its effectiveness on actual student reading growth using appropriate measures.
That's a perfect illustration of the shifting emphasis. It's a logical progression that matches the maturity and stability of the intervention itself. You wouldn't try to run a large randomized controlled trial, RCT, to prove effectiveness on a paper prototype. You build up to assessing effectiveness systematically.
This whole systematic approach, moving through phases, focusing on different quality criteria, it ultimately culminates in something more than just a working product, which brings us back to that twofold yield and the core knowledge contribution of EDR. The source material often shows this with a kind of schematic model, right? Something like intervention X, which has inputs leading to a process happening in a specific context Z leads to certain outcomes Y1, Y2, Yn. And crucially, studying this whole picture generates design principles or intervention theory. Can you break that model down for us? It sounds dense but important.
Yeah, that model, even though it looks a bit abstract, really captures the essence of EDR's dual purpose, the practical and the theoretical happening together. It emphasizes that an intervention, let's say our elementary reading app, Intervention X, isn't just a static product. It's a dynamic process that unfolds within a specific classroom or school, context Z. And that process is influenced by various inputs, things like the quality of the school's internet access, the specific devices students are using, the amount and type of teacher training provided, input process. All of these interact to influence how the app is actually used and ultimately lead to certain results or outcomes Y, like changes in reading fluency, comprehension scores, student motivation, etc.
Okay, so the intervention isn't isolated. It interacts with inputs and context to produce outcomes. Where does the theory part come in?
The theory part, the design principles or intervention theory, comes from analyzing that entire picture. It's about understanding the how and the why of the intervention's functioning. How did the inputs and the context shape the process? Why did certain features lead to specific outcomes? What conditions seemed necessary for success? By systematically studying this whole dynamic interplay, you distill the key learnings into those design principles, or maybe a more elaborate local intervention theory. This is the structured knowledge you can carry forward. It's not just about celebrating that you built a successful app, but deeply understanding the underlying mechanisms that made it successful in that context so you can apply that understanding intelligently in future similar situations. You're building your own and the field's library of effective design knowledge.
Okay, that term design principles keeps coming up as a key yield. It sounds like something incredibly valuable, especially for someone wanting to develop multiple educational products over time. What exactly are they and how do they help practically? I know the field even gives us a specific format for writing them.
Yes, design principles are really powerful and practical outputs of EDR. They're often defined as heuristic statements. A heuristic is essentially an experience-based suggestion, a rule of thumb, or a guideline for addressing a specific type of problem or achieving a certain goal.
So not a strict law, but strong advice.
Exactly. They offer guidance, but importantly, they don't offer guarantees because they explicitly acknowledge the uniqueness and variability of different contexts. They represent the accumulated, distilled wisdom from your rigorous design and research journey. And you're right, the field provides a very clear and useful format for articulating these principles, which makes them incredibly concrete. It often looks something like this. If you want to design intervention X for the purpose function Y in context Z, then you are best advised to give that intervention the characteristics A, B, and C. This part focuses on the substantive features, the what of the design itself, and to do that via procedures K, L, and M, this part focuses on the procedural aspects, the how of the design process, because of arguments P, Q, and R. This provides the rationale, the theoretical or empirical justification.
Wow, that is specific. It breaks it right down.
It does, and it helps ensure the principles are actionable and well justified. It forces you to be precise about the intervention, its goal, the context, the key features, the process used, and the reasoning behind it all.
You mentioned substantive and procedural characteristics.
Yes, that's a useful distinction.
Yeah.
Procedural design principles relate to the characteristics of the design approach or process itself. An example might be something like, if you want to design effective math software for elementary students, always involve teachers and students in co-design workshops from the initial concept phase. That's about how you design. Substantive design principles relate to the characteristics of the design artifact itself, the intervention. For example, if designing a math game for teaching fractions to third graders, the game should include multiple linked visual representations of fractions, example, number lines, area models, set models, rather than relying only on numerical symbols. That's about what the design should include. Often, a full design principle incorporates both.
Okay, that format makes it very tangible. Can we try crafting a concrete elementary classroom example using this format? Let's really nail down what a design principle looks like as a practical yield from an EDR project.
Absolutely. Let's take a common challenge. First graders often struggle with independent reading comprehension, especially as texts get a bit more complex. And as we know, teachers have very limited time for sustained one-on-one support. So your intervention X might be a guided reading companion app designed to be used independently by students after a group reading session. Its purpose Y is specifically to improve reading comprehension skills and foster independent reading habits among young learners. The context Z is diverse first-grade classrooms, likely with varying tech access and definitely with limited one-on-one teacher time available for follow-up.
Okay, got the setup. How might the principle look?
So, after going through iterative cycles of designing features, testing them with first graders, getting teacher feedback, analyzing student responses within the app, you might distill your findings into a design principle structured like this. If you want to design a guided reading companion app, X, for the purpose of improving reading comprehension and fostering independence, Y, and diverse first-grade classrooms with limited teacher time, Z, then you are best advised. Quote, to give that app the characteristics of A. Short scaffolded comprehension questions embedded directly within the text or appearing immediately after each short paragraph substantive. B. Providing immediate supportive audio feedback for both correct and incorrect answers, not just a visual checkmark substantive. And C. Including features like adjustable reading speed and font size options substantive.
Okay, those are the key features of the app itself. What about the process?
And to do that via procedures like KKI, conducting frequent, small group usability tests with representative first-grade students during development to ensure the interface is highly intuitive and minimizes frustration, procedural, and L, providing very clear, concise, maybe even printable teacher guides that allow for quick integration into existing reading routines with minimal prep time procedural.
Got it. And the because?
The rationale.
Because, P, this combination provides immediate personalized feedback that supports comprehension without requiring constant teacher intervention, thus fostering student autonomy. Q, it accommodates varied learning styles, reading paces, and potential visual accessibility needs common in early grades. And R, it demonstrably reduces teacher workload related to checking basic comprehension, freeing them up for more targeted instruction.
Wow, okay. That is incredibly precise and powerful. You're not just saying make a comprehension app. You're giving a detailed, research-backed blueprint for how to make an effective one for that specific context and clearly stating why those design choices are crucial based on your findings. That's truly actionable knowledge. Exactly. That's the goal of a well-formulated design principle.
But here's a big question. Can these findings, these highly specific design principles, actually be generalized? Or are they kind of stuck in the specific classroom or the few schools where they were developed? Can that principle for the first grade app apply elsewhere?
This is a really key point in EDR methodology, and the field addresses it very clearly. EDR typically doesn't aim for what's called statistical generalization, the kind you see in large-scale surveys or experiments where you try to generalize findings from a random sample to a much broader population, like saying X% of all third graders in the nation prefer this teaching method.
Okay, so not that kind of generalization. What kind then?
Instead, EDR usually aims for what's called analytical generalizability, or sometimes transferability. This means that the design principles or the local theories developed in one study need to be tested and refined through further research, particularly through replications or adaptations in different yet relevantly similar contexts. The crucial takeaway, often emphasized by influential educational researchers like Lee Cronbach, is something like this. When we give proper weight to local conditions, any generalization is a working hypothesis, not a conclusion.
A working hypothesis.
Exactly.
Yep.
Your design principles provide strong, evidence-based guidance, but they remain heuristic statements. They suggest promising directions rather than guaranteeing identical outcomes everywhere. Why? Because every classroom, every school, every group of students has its own unique characteristics, culture, resources, and constraints. A principle that worked beautifully in one suburban third-grade classroom might need thoughtful adaptation to work effectively in an urban kindergarten or a rural multi-grade classroom.
So, for you, the product developer, that carefully crafted design principle for the first grade reading app, it serves as a really strong working hypothesis if you decide to build, say, a similar app for second graders, or perhaps adapt it for a different school district with different demographics. It gives you a highly informed starting point, much better than guessing, but you'd still need to test and likely adapt it for that new context. It's not a universal, unchanging law.
Exactly. It's about building a robust, context-sensitive body of knowledge that grows in validity and applicability through careful cumulative research, through replication, adaptation, and refinement across various relevant settings. It's less about finding one single truth and more about building a set of increasingly reliable, context-aware guidelines for effective design.
Okay. Conducting EDR sounds incredibly hands-on, deeply embedded in the real world, and requires wearing multiple hats. It makes complete sense that the researcher is often, simultaneously, the designer, the evaluator, and sometimes even the implementer of the intervention they're studying.
It's very common.
But this deep involvement, couldn't it, theoretically at least, raise some questions about objectivity? How do researchers ensure they remain unbiased when they're so invested in the success of the thing they're creating and studying? It sounds like you could easily develop blind spots.
You're right, it is a lot of hats.
Yeah.
And managing potential bias is a valid and extremely important concern in EDR. However, researchers in this field are very aware of this challenge and have developed concrete strategies and best practices to address these potential conflicts of interest and maintain scientific rigor.
Okay, like what? What are the safeguards?
Well, several key measures are often employed. First, professional scrutiny. This means actively making your research process and findings open to critique and review from external experts, people outside of your immediate project team or institution. Getting fresh eyes and unbiased perspectives on your design choices, your data collection methods, and your interpretations is crucial. It's like having peer reviewers for your process, not just your final published paper.
Okay, external review. What else?
Second, the researcher needs to consciously shift their role or perspective as the project progresses. In the early stages, it's natural and necessary to have more of a creative designer mindset, generating ideas, brainstorming features, being optimistic. But as you move into evaluation phases, you need to consciously shift towards a more critical researcher perspective. This means rigorously evaluating what you've built, actively looking for flaws, seeking disconfirming evidence, and being objective about the results even if they aren't what you hoped for. This shift is often reflected in the increasing formality and rigor of the evaluation methods used in later cycles.
So, deliberately changing hats depending on the phase.
Exactly. Third, and this is foundational to any good research, is having a strong overall research design. This includes using what's called a strong chain of reasoning, where each step of your research, from the initial problem analysis to the final conclusions, is logically connected, explicitly documented, and methodologically sound. A key part of this strong design is triangulation. This is vital in EDR. It means using multiple data sources. For example, student test scores, observation notes, teacher interview transcripts, samples of student work, multiple data collection methods, for example, surveys, classroom observations, artifact analysis, focus groups, and sometimes even multiple investigators or analysts to look at the data. This helps you cross-check findings, get a more complete picture, and avoid bias that might come from relying on just one perspective or data type.
Using multiple lenses to see the whole picture.
Precisely. And finally, related to the strong design, is systematic documentation. This means rigorously and meticulously documenting every single step of the process. Every design decision and the rationale behind it, every development iteration, every evaluation method used, every finding, positive or negative, and every aspect of the implementation process. This detailed record-keeping provides transparency, allows others to scrutinize your work, and serves as an audit trail, proving the rigor of your process.
That makes a lot of sense. So putting it back in the elementary context, if you're both designing that new phonics game for first graders and then evaluating its effectiveness, you would need to actively invite other teachers or literacy specialists to review your game design critically. You'd need to use diverse data points, maybe student work samples showing phonics application, detailed observation checklists of students using the game, teacher logs, maybe even short student interviews, not just relying on your own general impressions or pre-post test scores alone. And you'd have to be completely transparent about your entire development and evaluation process.
Exactly. That combination of external scrutiny, diverse evidence through triangulation, and transparent documentation is your best defense against potential bias and ensures your findings are credible.
Okay, another challenge. EDR takes place in real-world settings, like actual elementary classrooms. And as anyone who has spent even a day in one knows, real-world settings are incredibly complex, dynamic, and full of unpredictable variables. It's definitely not a controlled, sterile lab environment. What kinds of challenges does conducting research in such messy, dynamic places present?
You're absolutely right. Classrooms are incredibly complex ecosystems. One significant challenge, especially early on, is that the researcher might initially be perceived as a cultural stranger in the school setting. You're coming into their space,
An outsider.
right? Building trust and rapport with the teachers, the school administrators, and crucially, the students, is paramount.
Yeah.
It takes time and genuine effort. You need to gain an insider perspective to truly understand the context, the existing routines, the school culture, the unspoken rules, the specific pressures teachers are under, the unique needs of that particular group of students. Without that deep contextual understanding, your intervention, no matter how well designed in theory, might simply not fit or might be implemented in ways you didn't intend.
So you need to understand the local culture.
Definitely. But at the same time, you have to maintain the necessary objectivity of an outsider researcher, remaining scientifically rigorous while being immersed in the context. It's a very delicate balancing act. And related to context, you have to recognize that what works beautifully in one fourth grade classroom in a well-resourced suburban district might face completely different challenges or might not work nearly as well in another fourth grade classroom across town. Maybe one with fewer resources, different student demographics, different levels of parent involvement, or different school-wide policies. Being adaptable, building those relationships, and deeply understanding these local nuances are absolutely key to the success and relevance of your intervention. You generally can't just parachute in with a prepackaged solution and expect it to magically fit everywhere without significant attention to context.
That really underscores the importance of that context Z in the design principles we talked about.
Okay, so given this iterative nature, the need to respond to real-world feedback and these unpredictable settings, it sounds like the research design itself has to be flexible, right? You can't just lock it down entirely at the beginning.
That's correct. Rigidity is often the enemy in EDR.
But how do EDR studies manage to be adaptable and responsive without becoming, weak or wishy-washy? How do you maintain scientific rigor while also being flexible? It sounds like a real tightrope walk.
It absolutely is a tightrope walk, but it's managed through careful planning and a concept often referred to as evolutionary planning. This means you start with a solid, well-thought-out initial research plan, but it's designed as a flexible framework that allows for adjustments in response to emerging field data and experiences at appropriate, pre-considered points or acceptable moments during the course of the study.
Evolutionary planning.
Oh.
So you don't rigidly stick to the initial plan if the data from your early prototype testing clearly tells you that a core component is failing badly or that a completely different approach might be needed. If you discover, for instance, that the technology platform you chose for your intervention is causing endless headaches for teachers, an evolutionary plan would allow you to pause, reassess, and potentially pivot to a different platform or delivery method rather than just pushing through stubbornly because it was in the original proposal. This adaptability also extends to the role of the researcher. As we discussed, sometimes you need to take on roles beyond just being a passive researcher. You might need to become more of a facilitator, a technical support person, an instructional coach, or a co-designer collaborating deeply with the teachers. The challenge, again, is to do this effectively while maintaining your scientific rigor and objectivity. You need a really sound understanding of research methodology to make prudent, data-informed changes, not just arbitrary shifts that undermine the study's validity. It's all about being intelligently responsive to the learning that inevitably emerges from engaging with the real-world context, rather than being unnecessarily constrained by an inflexible initial plan.
Can you give us one last elementary example of how this adaptability might play out in practice?
Certainly. Let's imagine you've planned a 3-week pilot implementation of a new project-based learning unit on community helpers for third graders. Your initial plan involves students conducting interviews with people in local businesses.
Okay.
After the first week, your observations and teacher feedback reveal significant logistical hurdles. Maybe arranging off-campus visits is proving impossible due to school policies or lack of parent volunteers. Or perhaps the third graders are struggling significantly with the interview skills needed, and the activity is causing more frustration than learning.
So the initial plan isn't working smoothly.
Right. An adaptable EDR design, guided by evolutionary planning, wouldn't just force everyone to push through with the failing component for the next 2 weeks just to stick to the original plan. Instead, it would allow you to pause, analyze the feedback and observation data, and make a reasoned adjustment. You might decide to pivot the activity. Perhaps you revise it to have students conduct virtual interviews by researching community helpers online and maybe Skyping with willing participants. Or maybe you decide to bring several community helpers into the classroom for a panel discussion instead. You document this change, the reasons for it, and then re-implement the revised activity. This requires flexibility, but also a sound understanding of research rigor to ensure you're making prudent changes based on evidence, always keeping the core learning objectives for the unit clearly in mind, not just making random shifts that weaken the overall study. It's about learning from the real world and then intelligently responding to improve the intervention's practicality and potential effectiveness. Hashtag tag outro.
And just like that, we've taken a really deep dive into educational design research. We've explored how this powerful methodology directly tackles that critical need, the need for educational solutions that are not only based on sound theory, but are also genuinely practical and effective when they hit the ground in real classrooms.
Bridging that gap.
Exactly. And for you, our listener, with your valuable background in elementary education and maybe that growing passion for product development, EDR offers an incredibly robust and rewarding framework. It helps ensure that your innovations, your great ideas, are deeply grounded in rigorous investigation, that they get iteratively refined with input from real users, those actual teachers and students, and that your work potentially contributes lasting knowledge back to the field, beyond just the product itself.
It really does transform the creation process. It moves it from something that can feel like a guessing game into a more systematic, evidence-based, and ultimately more impactful endeavor. You're building, you're learning, and you're sharing that learning all as part of the same cycle. It's a powerful engine for continuous improvement in education.
So, as you embark on designing the next great educational product for young learners, whether it's a new literacy tool, a cool STEM kit, or an innovative app to support social-emotional learning, maybe consider this final thought. What new design principle for elementary education might your next intervention help to uncover? How could your work, through the process of EDR, not just solve an immediate problem for one classroom or one school, but actually contribute a valuable piece to the larger puzzle of learning? Think about how your next creation could be more than just a tool. It could be a fundamental piece of research that helps all of us understand just a little bit better how children learn and how we can teach them even more effectively. What lasting contribution could you make?